Thank you very much for inviting me. Thank you all for coming. So yeah, as already mentioned, so today the title of my talk is Inference, Computation, and Games. And so really what this talk is going to be about is going to be about two sort of long-standing research campaigns that I've been on over the last few years. One of them is the use of comparative optimization, so sort of modeling multi-agent games routines of artificial agents as a tool for designing algorithms. And the second part will be on the sort of the relationships between Cholesky factorization and the conditioning of Gaussian processes. So the first part, again, that's on the comparative optimization. So what do I mean by comparative optimization? So we all know sort of single agent optimization, right? Where we single agent optimization, where we're concerned with a sort of single agent choosing a decision variable x, such as to minimize an objective f of x. And this is a sort of ubiquitous paradigm that we use for designing algorithms. So we come up with a function that we don't like, and then we say we come with a new algorithm for solving a problem by finding the x that minimizes this function. And typically in much of computational mathematics, the sort of basic workhorse algorithms for solving these problems is gradient descent. So something like this. Now, comparative optimization is a somewhat less, maybe less standard paradigm for designing algorithms, where instead of having just a single agent x and a single objective function f, we have at least two agents, x and y, that try to minimize their own respective objective functions. So here you can think of the cat being one agent and the mouse being the other one. And so they have obviously different objectives. And in particular, the loss of both of these objectives depends on both players' actions. So the loss of both players depends on both players' actions. And we are mostly interested in the case where these agents have conflicting goals, meaning that that what an outcome that is good for one of the agents is bad for the other and vice versa. Now, this is a much less sort of common or popular framework than ordinary optimization. However, it has many sort of important applications. So one of them being maybe the least surprising multi-agent reinforcement learning, where we are simply interested in sort of teaching agents to play competitive games. So in some sense, it's not surprising that if we want to teach agents to play competitive games, that the resulting optimization problems will have this competitive flavor. However, there's also the very classical methods in constrained and robust optimization, where we think of a second player that models either a Lagrange multiplier that penalizes us for violating constraints, or a sort of perturbation that penalizes us for lack of robustness. And finally, there has been a recent sort of surge of interest in these type of methods due to the success of adversarial machine learning, in particular generative adversarial networks. And now in the first sort of work I want to talk about is the development of a sort of trying to find a natural generalization of gradient descent to these comparative optimization algorithms. And this was joint work with Anima and Kumar. Now, again, we have seen the difference between ordinary optimization and comparative optimization. So we can ask ourselves now, what is the generalization of gradient descent to comparative optimization? And maybe the most common view, or the first thing that comes to mind, is simultaneous gradient descent. So instead of just having one agent play gradient descent, both agents now perform a gradient descent update on their respective loss function. However, this has a problem that diverges even for relatively simple games like this game X transpose Y, where sort of the Nash equilibrium, the optimal solution would be the point 0, 0. But if we actually run the simultaneous gradient descent, we would see this we see this sort of oscillatory and divergent behavior. And in some ways, these oscillations are really another instantiation of rock, paper, scissor, if you've ever played this hand game. And this has been a sort of this has been observed before, and it has motivated a bunch of sort of modification and tweaks and fixes to simultaneous gradient descent to try to make it better performant. For instance, optimism, proximal methods, augmentation, extra gradient, and the like. Now, instead of sort of trying to sort of go the route of one of these modifications, we wanted to ask ourselves we want to basically take a step back and ask ourselves, is gradient descent or simultaneous gradient descent the right generalization of gradient descent in the first place? And maybe there's another better generalization of it. And one sort of useful path of deriving such a generalization is this variational characterization of gradient descent, which means that the displacement, so the update of gradient descent can be obtained as the minimization of a local linear approximation, so kind of a model problem, together with a quadratic penalty that reflects our limited confidence in this local approximation. And by minimizing this sort of problem, this regularized linear problem, we obtain exactly the gradient descent update. And now this suggests a straightforward path to designing generalization to multiple agents, which means that now we want to have a linear approximate problem now, or a linear approximate game, so to speak, where we now again add a regularization of both agents and use the Nash equilibrium, the optimal solution of this game, as an update rule. And the sort of mathematical question that this leads us to is, how should we best linearize a game? Because if we say straightforward, okay, we had a linear approximation for one agent, then maybe we have a linear approximation for two agents, we find out that the two games, the two objective functions of the x and the y player are not coupled anymore. Because as you see here, the only term that involves the y in the loss function of player x is constant with respect to x. And the only term that involves an x in the loss function of player y is constant with respect to y. So in some sense, we can remove them without changing the optimization problem. And as a result, we are now in the situation where basically this local problem that the agents are solving is just is entirely independent. So it has lost all information about it being a competitive optimization problem. And and if we do this, we recover a simultaneous gradient descent. And sometimes the fact that the local problem has forgotten about the interaction, about the sort of competitive nature of the games, is arguably the reason why a simultaneous gradient descent performs so poorly even on simple problems. Now, an alternative generalization of a linear approximation for one agent is a multilinear approximation, meaning we would use a bilinear approximation for two agents and an n-linear approximation for n agents. And what this means is that now, on top of the sort of linear approximation that we've used so far, we are also adding this bilinear approximation that is obtained from the mixed Hessian, so the off-diagonal blocks of the Hessian matrix that contains only the derivatives, one derivative with respect to x and one with respect to y, but not the second derivatives in x or the second derivatives in y. And now this bilinear approximation is generally interactive in the sense that what is a good strategy in this local game for x depends on what y does, and what's a good strategy for y in this local game depends on what x does. Excuse me. And it turns out that this game has a unique Nash equilibrium, so a unique sort of optimal solution pair that one can compute using linear algebra. And we're going to talk about in a moment about how to do this computation. But for now, okay, at least there's a solution, and we can use this solution as an update rule. And this is competitive gradient descent, and we claim and argue that this is sort of the natural generalization of gradient descent to multiple agents. Now, before talking about the some more about the application,
I have a question for your update.
Sure.
Maybe previous slides.
Sorry.
Maybe previous slides. One more.
Oh.
Okay.
Wait.
Yeah. Here, bilinear approximation.
Yeah.
No, here I think even earlier. Maybe 18, I think. Or 17, maybe. Oh, here.
Yeah.
Okay, so for these both problems, for the x part, only the x is a variable, or both x and y are variables?
So what this really means is this is a sort of this is now a game, a non-zero sum game between these two agents.
Right.
So simultaneously, it's kind of like simultaneously x and y have x, the x player has to choose an x, and the y player has to choose a y. And x wants that when you plug the two y's into the top equation, x wants this to be as small as possible. And when you plug the two y's into the bottom equation, y wants this to be as small as possible.
Okay, but for example, for the top one, do you assume y is unknown or known?
So that's exactly the thing. Y is unknown.
Right.
The x player knows that y is trying to minimize the second equation.
Right.
And so that's why that's exactly this problem. So x kind of tries to incorporate the fact that x knows that y is also playing the same game.
I see. So somehow you have to jointly solve the two problems.
Exactly, and that is really what the Nash equilibrium comes into play. The Nash equilibrium is sort of a natural solution concept for this type of problem because it means it's a point where neither x nor y would be willing to change their solution after they've seen the other player's solution.
I see. So somehow some competitors knows the behavior of the other players.
Exactly.
Okay, got it. Thank you.
Thank you. And yeah, please feel free to ask questions. I can be flexible with the cutting some things to make the time work. It's more important that people understand what I talk about.
Sorry, Dr. Sheik, before you move on, I also have a question about, so how exactly are the users interacting? I remember in the slide you have the bilinear function as interactive. Is it the user that's interacting, or what exactly do you mean that it's interactive?
What I mean is that in this local problem here, what is a good decision for x now depends on what y does and vice versa. So basically, if I want to do well on this problem now as an x player, I have to think about what y is going to do. Because otherwise it can be that this x times y term here totally destroys me, basically. Whereas without this term, as an x player, I can just only do what I do and totally ignore the fact that there's a y player that also does something.
Got it. Thank you.
And so one sort of interesting, I guess, game theoretic interpretation of this update rule is the following. So one can equivalently write the update rule like this. This is just basically a block LU factorization. And now we could write down the matrix inverse in the form of a Neumann series. So this sort of matrix sequence on the right for a small enough spectral radius of A converges exactly to the inverse. And now if we use only the first partial sum of this Neumann series, that means that we ignore what the other agent is doing, and so we just play simultaneous gradient descent. If we use the second term of this, the second partial sum, that means that we play the optimal counter strategy to gradient descent. So we think the other agent is ignoring us. And if we use the third partial sum, then we think the other agent that we are ignoring them, and so on and so forth. So each partial summit of the Neumann series corresponds to an additional sort of layer of reflection of what the other agent thinks that we do, that they do, and so on and so forth. And of course, the problem is, like in the limit, then everyone is very confused, but that's exactly where sort of why I guess game theorists discovered the Nash equilibrium as a way to resolve this confusion and find a solution concept where we wouldn't even want to change our solution if we knew exactly what the other agent is doing. And this is exactly what we recover through this matrix inverse, when the limit of the Neumann series going to infinity. Now, so that's a sort of a more like maybe like a interesting interpretation, but the more fundamental mathematical question is like, how do we want to locally approximate these games? And in particular, why do we use the bilinear approximation and not the full Hessian, which also would be the dxx and dyyy terms, which would lead us to a sort of regularized Newton's method. And so there are three fundamental reasons why I believe that this is sort of the right way of locally approximating games. The first one is that, so why do we usually only do first order approximation, second order, third order? So all the first derivatives, all the second derivatives, or all the third derivatives. The reason is that they are rotationally invariant, meaning that if I change my coordinate system, I compute my local approximation in the new coordinate system, and then I change back, is the same as if I had used my original coordinate system. But now if we have two players, for instance, changing a coordinate system could mean like taking a decision variable from player X and giving it to Y, and a decision variable from player Y and giving it to X by applying a rotation, for instance, to our coordinate system, to the joint coordinate system. Now this is not the same game anymore, but it's an entirely different game because we have changed the rules. Like you give a rook from white to black and you give a queen from black to white. I mean, you've changed the game. You haven't just written down a different way. And so the only sort of transformations that we want to be invariant to are the transformations within each player strategy space. So transformations that only involve the decision space of X or only involve the decision space of Y. And these sort of bilinear, more generally tensorial orders of approximation exactly have this property. The second nice property is that even for non-convex problems, CGD is guaranteed to be, the CGD update is guaranteed to be local optima. So we know that for non-convex problems, Newton's method can be equally attracted by sort of local worst, so local maxima as well as local minima. And the benefit of this bilinear approximation is that it still allows us to only be attracted by sort of for the agents only to try to sort of locally minimize, even for sort of arbitrary non-convex objective functions. And finally, maybe more practical concern is that in many applications, this mixed Hessian might be defined, for instance, in a GAN with ReLU activations, whereas the dxx or dyyy would not be defined, because then two derivatives fall on a single ReLU and we have a sort of a Dirac measure as a result. Now, so for the convergence, the main sort of convergence result, which is, I mean, it's not a very deep result, it's just basically tailoring and then keeping track of terms, is that we can say that as long as the step size is smaller than the curvature in X or in Y, we have a local conversion of the convex, we have local conversions to saddle points. Where the main difference to other modifications like extra gradient and so on is that they also need eta to be smaller than this mixed derivative dxy. And so that means that that as the game becomes very interactive, so what the player X does really strongly affects what the player Y does and so forth, methods like extra gradient have to adapt to this by reducing their step size, which CGD does not have to do. And this particularly ties nicely with the sort of next problem that maybe some of you already had in mind, that CGD needs us to compute the inverse of a matrix. So for instance, this matrix here, identity plus eta square, dxy, dyx. So this is in the zero-sum case. And what's very nice now is that basically whenever eta times dxy is small, this inverse can be computed very quickly using conjugate gradient methods, or more general Cryo subspace methods. And it's only when this eta times dxy is large that we actually have a substantial overhead of using CGD. But that is exactly the case where extra gradient and similar methods do not converge anymore at all. So there's like if we choose a sort of a target accuracy in our local solve, we have an automatic adaptation of the amount of computation that we invest at each iteration. And so now I'm briefly going to mention some sort of cases where we or other groups have. What was the question?
Yeah, and so before we go to next part, or question clarify.
Yeah.
So on your convergence complexity here.
Yeah.
So I think it's this like a general statement, right? But I'm curious, what kind of assumptions you make to this problem for the convergence? Like, do you need to assume like a convexity or concavity on this problem?
So this is like local convergence to saddle point implicitly assumes kind of local convexity. Like if you have a smooth problem, because you assume that the curvature is positive for it to be a saddle point.
Okay, local convergence. And the saddle point is a global sense, or
that has to be, that local sense is enough. But basically what happens is you assume you have the curvature in the right direction, and then you start close enough, and then you just show that you never walk out of this local neighborhood. So that's
okay. So the saddle point is also local.
Yeah.
Oh, I see. Okay.
But it's not, I mean, I'm not claiming, this is not actually a very deep thing. It's just what you get from the classic sort of stability analysis type of tools, basically.
Got it. Yeah, thanks.
And so now I'm briefly going to give a sort of a gamut of cases where, yeah, either we or other researchers have been applying these techniques. So one thing that we did relatively early on together with Honkai, who's now a PhD student at Caltech, was sort of study the performance of CGD on GANs. And so in particular, we were studying whether there's some sort of particular case of implicit regularization that arises from using CGD. And so what we did to this end, we used a WGAN-GP model on CIFAR10. We removed the gradient penalty, and we trained with CGD. And we observed that this, in terms of inception score and FID, leads to better results than the sort of the previous sort of GP WGAN-GP model that was trained with Adam, but still had the sort of gradient penalty as a regularizer. And we're still sort of trying to, so this worked very well on CIFAR10. So we're still in the process of trying to sort of scale up these results to larger GANs and something like ImageNet or so. So far this, I mean, we have not been able to do so that's like ongoing work. But at least, I mean, the reason why we think there is something there is that if we had these like very sort of clean results when we applied it to GANs on CIFAR10 type scale. Another sort of very recent application is for deep learning with physical constraints. So some of you may be familiar with what's called PINs, so physics-informed neural networks, where one basically wants to solve a PDE by replacing the solution with a neural network and then puts a sort of a penalty on the residual of the PDE. So we found that if we instead use a sort of discriminator generator type of architecture, so now we have a sort of a discriminator D that for each point tries to basically predict whether the PDE is going to be undershot or overshot, so whether the residual is positive or negative. And so we replace the penalty with this kind of nonlinear Lagrangian multiplier. And we observe that basically because this allows us to avoid the sort of squaring of the differential operator that is inherent in penalty-based methods, we observe that we can oftentimes get much better, much higher accuracy when using this sort of competitive formulation together with CGD. Another application, this was I was not involved in this, was by collaborators in computer graphics, is for constraint optimization, where again one wants to use Lagrangian duality and then turn the sort of Lagrange multiplier into a second player and optimize using CGD. And so these were sort of geometric optimization problems where the goal is to minimize the Willmore energy, which is the notion of smoothness, such that subject to the constraint that these triangles line up to a surface in a prescribed form. And so here on the left, you see, for example, an augmented Lagrangian type approach. And what Yusuf and his collaborators observed is that even though this method eventually converges, this sort of, it can take a long time for these kind of residual oscillations to average out. And in particular, also the tuning of the penalty in the augmented Lagrangian method is quite finicky. And so you see when you scroll a bit further that even at the very end, there's still some sort of residual wobbling. And in comparison, they observe that with CGD, I mean, they converge within a much smaller number of iterations to the Eibor norm. And you'll see here at the very end of this video, this basically is converged to the Eibor norm, so there's no residual wobbling. And finally, the last application I want to mention is by Manish Prajapat and his collaborators, where they extend this to policy gradient. And basically what they observe is that when training agents, instead of sort of ordinary policy gradient with a sort of a CGD version of policy gradient, again, the sort of competitively trained agent ends up doing better at playing the game. In particular, at sort of learns sort of more subtle behavior like defending against an attacker in this Markov soccer game. So the summary, so this first part was about extending gradient descent to competitive optimization. We mentioned that, or we argued that this bilinear approximation is the natural choice for competitive games, and we show applications to GANs, graphics, multi-agent RL. And there's some further work on incorporating equality constraint, understanding why GANs work, and also like extensions to beyond two players that unfortunately I didn't have the time to talk here, but you're welcome to check out these papers on my webpage. Okay, so any questions for this part? Otherwise, I'm going to move on to the second part, and that will be quite a change of scenery.
Hi there.
Hi.
I actually have a question about this application for this physics-informed neural network.
Hmm?
Do you mind to just like go through one example to see how you can improve compare with the traditional formulation in terms of results?
You mean in terms of the numerical results?
Yes.
Yeah, so what we basically, I mean, I think the main takeaway is that, so even on very simple problems like Poisson type problems, pins tend to not really converge to high accuracy. So, I mean, so the I guess the highest accuracy that I've seen in the literature is something like maybe 10 to the minus 4 or something of that order. And that I think is maybe the main sort of benefit so far, that with a suitable sort of CGD based optimization we can train pins to up to about 10 to the minus 6 accuracy.
So do you think the main reason is you no longer use the square? That's one of the factor.
Yes, that's my go-to sort of hypothesis why we see these improvements.
Mm-hmm. Okay. All right. Thank you.
And another thing that might also be helpful is that, again, because with the CGD in some sense it's a bit like, is partly, I mean, it uses some of the curvature information, this dxy curvature information, but at the same time it doesn't have the same tendency to get stuck in sort of arbitrary critical points as a Newton-based method would. So I think that's the other sort of source of benefits of CGD for these type of problems.
All right, thank you.
Thank you. And now, so for the second part, we're going to have a bit of a change of setting. So this is going to be a slightly more traditional applied math in a sense, but I'd say with a twist, which is about the heuristic view on Cholesky factorization. And so just to sort of provide some grounding of some setting where the things I'm going to talk about hold rigorously, I'm going to start with that, but I will mention that many of these algorithms, sort of empirically, they seem to apply to significantly broader scope. We just don't necessarily know how to prove things rigorously in these scopes. And so what we're going to be dealing with is so we assume we're given a domain omega and Rd, something like this. And then we take a linear elliptic PDE, where at least for the instantiation that I'm mostly going to talk about here, we want to assume that the order of the PDE is larger than the spatial dimension. So for instance, for 2D, you could think of something like the bilaplasian. But I want to emphasize that this sort of class of PDEs that we're considering sort of captures much more general equations with sort of arbitrarily rough coefficients, arbitrarily high order, and so on and so forth. And there are also variants of the results that hold without this order bigger than D constraint. But that's just so for concreteness, that's going to be one instance where these things are going to hold. And now in this setting, what we're going to do is we're going to have a look at the Green's function of the PDE, which means the inverse of the partial differential operator in the sense of convolution. And so here you've seen me plot one sort of column, plot this Green's function for different values of y for one value of x fixed in the middle. And now we're going to assume that we're given a set of points xi in this domain. And these points are roughly equally spread out, meaning that the ratio between either the smallest distance between 2 points or a point in the boundary and the biggest sort of gap without any points, this ratio is uniformly bounded. And now we plug pairs of points into our Green's function to obtain the sort of discretized Green's function, what I would call the Green's matrix. And here it is important, if you want to use these pointwise evaluations, that we have the assumption that the order of the PDE is larger than the spatial dimension, since otherwise the Green function has a singularity. And so why should you care about these objects? Well, There's some sort of reasons in more computational physics type application where simply, I mean, the physical object we're dealing with might be governed by an elliptic partial differential equation, and then G is sort of the solution operator. So G describes how objects abiding by this PDE look like. In statistics and machine learning, it turns out that G's of this structure are very useful as covariance functions for smooth Gaussian processes, or equivalently as kernel functions to be used inside of a kernel trig. And you see that here this property that sort of the maximum of this Green's function is obtained as for x equal to y, and then as y moves away from x, sort of the value is dropping. That's exactly the behavior of a random smooth function, where for two nearby points they will be very strongly correlated, but as the points get further and further away from each other, their correlation becomes weaker. And in these applications, we're typically interested in computing matrix vector products with this kernel matrix, or to compute sort of to compute matrix vector inverse products. Similarly, in Gaussian post statistics, again, we're interested in computing the conditional mean, the conditional covariance, in computing log determinants, or sampling from this Gaussian process. And the problem in doing all these operations is that these matrices are dense. So even storing it a priori takes n squared complexity, and then we have this n squared to n cubed complexity for basically all the operations we're interested in if we want to use density algebra. And that makes sort of density algebra prohibitive for problems maybe of the order 10 to the 5 and larger. And so we need faster approximate methods. And this is a classical topic in applied mathematics. So there have been many sort of methods proposed in literature, including multigrid, wavelets, fast multipole methods, off-diagonal low rank, and so on. So this is, I mean, this is one of the bread and butter topics of applied mathematics, I would say. And so you could, given that, you could wonder, why am I still here talking to you about this? So first of all, so what this talk is largely going to be about is it's going to be about ways of computing approximate Cholesky factors of these matrices in near linear complexity, near linear in the number of degrees of freedom, and scaling only logarithmically in the target accuracy. And for this problem class, this is the sort of best rigorous result on the trade-off between accuracy and computational complexity. And the algorithms are also simple to implement. They're easy to parallelize, and they're quite performant in practice. And finally, the way these algorithms are developed is through a sort of a connection between Cholesky factorization and sort of conditioning of Gaussian processes that I think is interesting in its own right and might still yield further insights down the road. And so now I'm going to present at least some of a suite of algorithms that are sort of that are all going to rely on this common mathematical structure. And the first algorithm, which was in the beginning, at least for me, of working on this topic, is this algorithm for the sparse Cholesky factorization of the matrix theta. And so remind ourselves, the Cholesky factorization means that we write our matrix as the product of a lower triangular matrix and its transpose. And so the method I'm going to describe consists of 3 simple steps. In the first step, we're going to reorder the rows and columns of theta, because as you can already tell, lower triangularity is only defined with respect to a given ordering. So there should be a way to order the rows and columns in such a way as to be the most effective in computing this factorization. Then we are going to select a sparsity pattern that is a subset of the entries of the matrix, because we want to have near linear complexity algorithms, so we cannot even afford to write down the full matrix. So from the beginning, we have to restrict our attention to only a near linear number of entries. And finally, we're going to do Gaussian elimination restricted to the sparsity pattern. And so let me begin by walking you through this ordering and sparsity pattern. So remind ourselves that the ordering of the rows and columns really corresponds to ordering of the point, because each row and column of this matrix corresponds to a point in the domain. And so we're going to use what is called the maximum ordering, which means that we successively select the point, that is furthest away from the points that we have already selected. And as we do this, we keep track of this Li, the length scale of a point I, which is the distance that it had to the closest point that was selected before. And so we keep doing this, and we already observed that this sort of length scales of the point is getting smaller and smaller as we have selected more and more points. And then we order the rows and columns in the order corresponding to the in the order in which we have selected the corresponding points. And now we want to select the sparsity pattern. What we are going to do, we are going to select the sparsity pattern column by column. And so again, each column corresponds to the possible interaction of 1 degree of freedom, 1 point, with possibly all the other points. And so we say that we add an interaction to the sparsity pattern in a given column if the distance between the point corresponding to the column and the point with which it's supposed to interact with is smaller than a tuning parameter rho times the length scale. And so rho allows us to trade off accuracy versus computational complexity. And now we see that because this length scale becomes smaller and smaller as we select more and more points, we see that the columns that we're adding to the sparsity pattern similarly become sparser and sparser. And by a sort of harmonic sum type argument, we can actually show that the total number of non-zeros scales only linearly in n for a fixed row.
So, sorry, can I
Yeah.
have a quick question? Just clarify. So it's a given matrix theta. What is the xi again?
The xi are the points that we use to construct it. Remember, we construct the sorry. Here we construct this matrix theta by plugging in pairs of points.
Oh.
Into the covariance function. So they're kind of like the if you want to think of this as discretization, they're the physical locations of the local discretization points.
So this is only for the green matrix, not general matrix. Is that right?
Exactly. Yes. So that's like, I mean, all these methods that are doing better than n squared, they have to use some sort of special structure of these matrices.
Okay.
And that's how, for us, the special structure of the matrix enters the algorithm.
Okay, that makes sense. Thanks.
Thanks. Yeah, and thanks for the question.
So can I follow up with another question? So I understand your strategy is primarily for this green function trigger an induced matrix. So what's your abstract assumption about this green function? I mean, how general this can be applied, your particular strategy?
So in terms of rigorous proofs, I mean, this is
say like what assumption you have for this G? What's the key assumption you have about this G?
The assumption on the G is that it's the Green's function of an elliptic PDE with directly boundary conditioned. And so, and I mean, here you see the exact definition, right? It's a map from H0S to H minus S that is continuous, symmetric, positive, definite, and local. So that's not necessarily maybe the most intuitive thing to think about. So in practical terms, we actually find that this method works quite well also on, for instance, Matern type kernels, which are closely related to the Green's functions of elliptic PDEs. And so in some sense, from my experience in practice, this method tends to work well for kernels that have this kind of like have a cusp at the diagonal and then decay kind of smoothly towards zero as the distance between the points increases.
But do you, I guess the faster decay to zero, the more efficient the algorithm will be. Right?
No. That's exactly the important thing. Even our algorithm is much more accurate than what you could get just by truncating. In particular, if you notice, like, I mean, this decay is on the physical scale. Like, it doesn't depend on your discretization. So as you add more and more points, you'll have a like very, very dense matrix with a sort of the number of basically points that or entries that have non-zero or non-negligible values will be still of the order n squared. So it's not just using the sort of the sparsity you get from truncating.
All right.
Thank you. And so now we have come up with this, sparsity set. And now what we're going to do is we're going to simply do incomplete Cholesky factorization, meaning that we set all the entries outside of the sparsity set to 0, so we have never even had to compute them in the first place. And then we do Cholesky factorization, but we skip any operation that involves entries outside of the sparsity set. And so here on the right, you see sort of how the sort of memory access pattern of this factorization would look like, and in particular that it is sped up a lot because further to the right, where things are getting sparser, there are much fewer operations to perform. And again, the number of operations that this algorithm performs is only, scales only near linearly with n. And now you should wonder, why should this work? Because we have set all but near linearly many entries of this dense matrix to 0, so we ignored almost all of its entries. And then afterwards, we have skipped almost all of the steps in the Cholesky factorization. However, I'm claiming that we can prove rigorously that the approximation error will decay exponentially in rho. Even though each of these two approximations, the truncation and the sort of incomplete factorization, are very brutal approximations that by themselves would incur enormous error. And so to understand this, we can first just say, okay, imagine we just compute the dense Cholesky factor of this matrix in the ordering, and we see how it looks like. And so for that, it's helpful to remember that in the sort of literature on sparse U and sparse Cholesky factorization, there's this phenomenon called fill-in, where people are typically observing that even if you start with a sparse matrix, as you're doing your factorization, the factors will become denser and denser. So something like you see here, right? You start with a sparse matrix, but its Cholesky factors are going to be dense. Now it turns out that for our dense matrix, an opposite phenomenon holds, and this is a new observation, where if you start with a dense matrix and you do the Cholesky factorization, the result is actually almost sparse. So the entries are shown on a log 10 scale. So the gray ones are close to 0. And now we can, this was an observation that hadn't been really made in the sort of classical numerical linear algebra reasoning that is very much focused on sort of this like graph structure of sparsity and therefore the fill-in phenomenon. But it's actually quite, it's almost obvious when one takes a certain pluralistic interpretation of the Cholesky factorization. And so to this end, we remind ourselves that the Cholesky factorization of the covariance matrix of the Gaussian process is basically the iterative application of this matrix identity here. So basically, as you're Cholesky factorizing, you apply this matrix identity, then you apply it again to this lower right block here, and you keep doing this, and then you collect the left and the right factors all to one lower and upper triangular matrix. Now it turns out that these are exactly the formulas for the conditional expectation and the conditional covariance of the Gaussian process. In particular, the near independence of this Gaussian process X is equivalent to almost sparse Cholesky factors of theta. So that means that whenever we can find a stochastic process that is maybe densely correlated, but where after conditioning on the right variables, we see a conditional independence or near independence, this immediately implies the existence of a dense covariance matrix that has a sparse Cholesky factorization. And in fact, in the spatial statistics literature, people have long been observing a sort of a heuristic or a phenomenon that has pointed towards the conditional near dependence of these smooth function priors that we are concerned with here. And this is something called the screening effect. And that simply means that if you have a smooth function and you want to know, and you condition it on a point close to the red point, then this conditioning of the point close to the red point is going to sort of shield the points further away from the red point from the correlation. And so we see here in gray, these are gray points, the big gray points are the points that we condition on. And as we condition on more and more points, the conditional correlation of the red point shrinks and shrinks. So the correlation like shrinks and shrinks. And this is really the, in some sense, this like ordering that we have chosen is chosen in such a way as to maximize this effect by spreading out the points equally. And then the sparsity pattern is chosen in such a way as that we only keep sort of nearest neighbors within a radius that is of the order of this conditional correlation length. And we can prove these rigorously by relating them to recent results on operator adaptive wavelets and numerical homogenization, where basically we also can think of this sort of Maximin ordering as kind of like a very rudimentary wavelet basis, where sort of the closest wavelet level are only a few points. Then as we add a few more points, this is like the next wavelet level, and so on and so forth. So I don't have the time to go over the background of the proof here. But yeah, so this basically tapping into and also extending these results on operator adaptive wavelets allows us to obtain rigorous errors complexity results. And so the summary of this is that we can now Cholesky factorize these matrices at near-linear complexity. And in fact, this was up to improvements that I'm going to talk about now. And this was sort of the new best as to the complexity for these set of problems. And now there are some, in the interest of time, I won't have the time to sort of run like deal in detail with all the sort of algorithms from the suite. So I'm only going to glance very briefly over the next two projects. So one of these projects is the reconstruction from black box solvers, which means that now we again want to compute the Cholesky factor of the theta, but we assume that we only have access to matrix vector product and we cannot select individual entries. So for instance, we could assume that we have some sort of legacy solver or even a physical experiment that allows us to evaluate matrix vector products, but not access individual entries at a low cost. And so what we can then do, we can show that from only a logarithmic number of matrix vector product, we can recover this Cholesky factor, even though the eigen decomposition would need a sort of polynomial number in the target accuracy. And so this is based on some ideas related to graph coloring, and I'm not going to go into detail here. I'll leave it at that. Another thing, so far we have talked about the Cholesky factorization of this dense theta, which you can think of the discretized inverse stiffness matrix. Maybe it's not so surprising that there exists a similar pattern also for computing sparse factors of the sparse factors of the analog of the stiffness matrix, so the theta inverse, which you can think of as a discretized differential operator as opposed to the discretized integral operator. And so again, this gives us a direct path to a fast solver for elliptic PDEs, where we just determine this ordering sparsity pattern a priori, and then do again this I equals 0 now on the discretized differential operator as opposed to the integral operator. And it actually turns out that we're able to, so that was really mostly Zhong Chen's work to implement this in a performant way using parallelism and so on and so forth. And then it turns out that the resulting solver is competitive with established algebraic multigrid libraries like AMGCL or Trillinos. And so that is, I think that I found that very satisfying, because usually with these kind of like maybe more like mathematically motivated so methods, it can be very frustrating that one keeps getting beaten by sort of older methods that are just very well implemented. And so that was very satisfying to see that here one can actually get to the point of really competing with these established libraries. And now the last point that I want to talk about in a bit more detail is an approach for the sparse Cholesky factorization based on KL minimization. So we've just seen that we were able to compute sparse Cholesky factors of theta by doing this incomplete Cholesky factorization on theta. And as I just brushed over, we can also compute sparse Cholesky factors of theta inverse by the incomplete Cholesky factorization of theta inverse. Now, it turns out that the sparsity pattern for theta inverse is a bit sparser than that for theta. And so in principle, we would really like to be able to, even if we're given access to entries of theta, so the integral operator, we would like to be able to directly compute approximate factorization of theta inverse. And so at first I tried this for a while using some kind of analogs of Gaussian elimination. In principle, this works. One can even probably prove something about it, but it turns out to be very unstable in practice. So it was not really practically useful. And so the question was then, are there other ways of computing Cholesky factorizations? And in particular, one question was like, is there a way to sort of set up optimization problems that are trying to obtain the optimal approximate Cholesky factor? And a natural way of sort of deciding what the optimal one is to use a probabilistic, because we think of them as covariance matrices of Gaussian processes, is to use a probabilistic notion of similarity. For instance, the KL divergence between the original Gaussian process and the Gaussian process implied by our inverse Cholesky factorization. And at first that seems quite daunting, and it doesn't necessarily seem obvious that one can come up with a competitive method for numerical linear algebra by solving this sort of non-quadratic optimization problem. But there's some really nice magic happening. So we write down the closed form expression for the KL divergence, Kullback-Leibler divergence between the two Gaussian processes. So this is just a standard sort of formula. And now we observe three things. So we first observe that both the log determinant and the n do not depend on our optimization variable on the L hat. So we can directly remove them from the problem without changing the optimal point. And then we can also use the cyclic property of the trace in order to move around the L hat from the left of the trace expressions to the right. And if we write this out now, we observe that actually this optimization problem decouples, meaning that we can write this as a sum where each summand only depends on a single column of L. Or more exactly on the sort of entries within the sparsity pattern of that single column of L. So I should maybe have mentioned, yeah, so we're optimizing here over all L's in this S, meaning over all the L's that have a given sparsity pattern. And using this decomposition, we can come up with a closed form for the optimal optimal in KL divergence, sparse inverse Cholesky factor of theta. And afterwards, it turns out that actually this update rule without this sort of KL optimality had been discovered without them knowing of each other in multiple different communities. So this can be seen as a form of Vecchi approximation through the spatial statistic lens. It can also be seen as a factorized sparse approximate inverse, where it was obtained as a minimizer of the Kaporian condition number, or a sort of Frobenius norm Frobenius norm fidelity term with a diagonal scaling constraint. And finally, sort of nonlinear version of this has been studied by Yusuf Mazouk and his group in the context of nonlinear transport maps. And then there's some additional sort of algorithmic trickery one can do to bring down the cost of factorization. So I won't have time to talk about this. I want to briefly mention some of the limitations of the screening effect-based methods, which is one is that if our points start having like bigger gaps or smaller distance to each other, there's a slight deterioration of the screening effect. And a bigger concern is that if we're using this on something like a Maturin type covariance function where we don't have a directly boundary conditions, we will see some sort of loss of accuracy close to the sort of boundary of the domain where we have measurements. Another limitation that fortunately we were able to resolve is the is a problem of adding, like basically if you want to apply this not just to a matrix theta, but to the sum of theta and maybe a diagonal term. So there we found a trick around it, which is quite relevant for spatial statistics, where these sort of sums of processes, they can be considered as a latent true process and an additive measurement error, for instance. And then we see that this method is also performed in practice, can be scaled to sort of millions of degrees of freedom, while still achieving very fast sort of timings for the factorization, even on a single core. And when comparing to established techniques like HSS matrices, one thing that is a particularly nice property is that in the low accuracy regime, HSS matrices have the problem that they tend to lose the positive definiteness of the kernel function. Whereas here, because we're using this sort of optimization-based criterion, we can never use positive definiteness, because positive definiteness is associated with infinite KL divergence. So there's sort of some built-in stability that allows us to beat HSS-based methods particularly strongly on in the sort of low accuracy and low computational budget regime. So in the summary of this part, we compute these optimal Cholesky factors, which allows us to further bring down the computational complexity of solving the corresponding integral equations. And it can be computed embarrassingly parallel because the optimization problem decouples over the contribution to the different columns. And there's some further ongoing work on using KL minimization for nonlinear PDEs, on screening-based methods for nonlinear transport maps, and also on using ideas from experimental design to sort of adaptively design these sparsity sets. But I don't think I have time to talk about this here, and so instead I'm going to finish and ask if there are any more questions.
Okay, thanks a lot for the very, very nice talk. A lot of stuff there. Thank you.